Hello dear students, welcome to the lecture 7 of software engineering course. Today's topic is design and implementation. The topics we are going to cover today are
Object-oriented design using the UML. Design patterns. Implementation issues.
and open source development. Design and implementation.
Software design and implementation is the stage in the software engineering process at which an executable software system is developed.
This is more likely the stage that every one of us is most interested in. At this stage, we are producing the executable software system. It can be a website, it can be a desktop application, it can be a mobile application and such. So you see executable software system. Okay, this is the keyword.
Software design and implementation activities are invariably interleaved. Software design is a creative activity in which you identify software components and their relationships, based on a customer's requirements. Implementation is the process of realizing the design as a program.
Okay, build or buy.
In a wide range of domains, it is now possible to buy off-the-shelf systems (COTS) that can be adapted and tailored to the user's requirements. For example, if you want to implement a medical records system, you can buy a package that is already used in hospitals. It can be cheaper and faster to use this approach rather than developing a system in a conventional programming language.
Okay, this is so true. Usually, companies are always buying such ready systems as a package because they are being tested and they are being fixed and they are being cheaper. Okay. Because developing a software and keeping maintenance from scratch is extremely expensive when compared to selling in as a bulk and just tuning the software for the special requirements of a company. For example, we are purchasing a student management system from a company which sells student management system to many schools. Okay, it is the same approach.
When you develop an application in this way, the design process becomes concerned with how to use the configuration features of that system to deliver the system requirements.
So you will be likely to work in a company that is producing software for masses. Okay. And when you develop an application in this way, the design process becomes concerned with how to use the configuration features of the system to develop the system requirements. This is important.
An object-oriented design process. Structured object-oriented design processes involve developing a number of different system models. They require a lot of effort for development and maintenance of these models and, for small systems, this may not be cost-effective. However, for large systems developed by different groups, design models are an important communication mechanism.
Okay, this is important. Let's read it again.
However, for large systems developed by different groups, design models are an important communication mechanism.
Okay, process stages.
Process stages. There are a variety of different object-oriented design processes that depend on the organization using the process. Common activities in these processes include: define the context and modes of use of the system, design the system architecture, identify the principal system objects, develop design models, specify object interfaces. Process illustrated here using a design for a wilderness weather station.
Okay, we will see more about wilderness weather station.
System context and interactions. Understanding the relationships between the software that is being designed and its external environment is essential for deciding how to provide the required system functionality and how to structure the system to communicate with its environment. Understanding of the context also lets you establish the boundaries of the system. Setting the system boundaries helps you decide what features are implemented in the system being designed and what features are in other associated systems. Context and interaction models. A system context model is a structural model that demonstrates the other systems in the environment of the system being developed. An interaction model is a dynamic model that shows how the system interacts with its environment as it is used.
Okay, so this is the system context for the weather station. Let's look with weather information system here. They have one-to-one relation with control system. So there is one weather information system, one control system, and one satellite. And weather information system has one-to-many weather stations. So a lot of weather stations are linked to one control system, one weather information system, and one satellite. So each of these components or systems have one-to-many connections to weather stations. Okay, weather stations can be thought as mobile stations that you can put everywhere and move around them. It totally depends on your construction and design approach. However, this is how this wilderness weather station is designed as context. Okay. So weather station use cases. Weather information system generates report weather and report status. So these are the methods that we can execute in these systems: generate report weather and generate report status. And control system has these commands: restart, shutdown, reconfigure, power save, and remote control. This is the use cases, and this is the system context. Okay. So let's see the use case description. This is the tabular view of the report weather. Report weather is a method here. Okay, so this is the tabular description of use case description. System weather station. So use case is report weather. This is the method, and actors are weather information system and weather station. So the description, let's read it.
The weather station sends a summary of the weather data that has been collected from the instruments in the collection period to the weather information system. The data sent are the maximum, minimum, and average ground and air temperatures, the maximum, minimum, and average air pressures, the maximum, minimum, and average wind speeds, the total rainfall, and the wind direction as sampled at 5-minute intervals.
Okay, so these are all single values, and the wind direction is a continuous value which is sampled at 5-minute intervals. Okay, so this is the description of this use case, and what triggers this use case report to be generated,
The weather information system establishes a satellite communication link with the weather station and requests transmission of the data.
Okay, so this is the stimulus of the use case, and what is the response?
The summarized data is sent to the weather information system. Weather stations are usually asked to report once per hour, but this frequency may differ from one station to another and may be modified in the future.
Okay, so let's start the architectural design.
Architectural design. Once interactions between the system and its environment have been understood, you use this information for designing the system architecture. You identify the major components that make up the system and their interactions, and then may organize the components using an architectural pattern such as a layered or client-server model. The weather station is composed of independent subsystems that communicate by broadcasting messages on a common infrastructure.
Okay, so high-level architecture of the weather station is like this. Okay, there is subsystem fault manager if an error happens, subsystem communications, subsystem configuration manager, subsystem data collection, subsystem power manager, subsystem instruments, and they all are connected to communication link. Okay, this is the high-level architecture of the weather station. And let's see the architecture of the data collection system. It is this subsystem. It is like this. There is a receiver. Receiver gets the weather data and it goes to the transmitter. And let's see the object class identification.
Identifying object classes is often a difficult part of object-oriented design. There is no magic formula for object identification. It relies on the skill, experience, and domain knowledge of system designers. Object identification is an iterative process. You are unlikely to get it right first time.
Approaches to identification.
Use a grammatical approach based on a natural language description of the system, used in Hood-OOD method.
Okay, let's check this out.
Hood Hierarchic Object-Oriented Design is a detailed software design method. It is based on hierarchical decomposition of a software problem. It comprises textual and graphical representations of the design. Hood was initially created for the European Space Agency and is used in such varied domains as aerospace, Eurofighter Typhoon, Helios 2 Earth observation ground control, Ariane 5 onboard computer, ground transportation, and nuclear plants.
Okay, there is a page for this. Okay, you see this is so early design approach.
Hood is a method of hierarchical decomposition of the design into software units based on identification of objects, classes and operations reflecting problem domain entities or more abstract objects related to digital programming entities. It is intended for the architectural design, detailed design and coding for software to be developed in programming languages such as Ada, C, or Fortran, as well as in object-oriented languages such as C++, Ada 95 or Eiffel.
So you see the Hood was developed in 1987.
The Hood method was developed in 1987 under European Space Agency (ESA) contract as 0/1 to 1890/86 NL per mega-ampere by a consortium of CC, CRE A.S. and Matra Marconi Space. Hood has been selected by ESA projects as the design method for the architectural design phase. Since, Hood has been selected by large, complex or long-lived project from aerospace, defense and industry.
Okay, so you see this website is extremely old. Maybe we can see some images related to this. Okay, let's continue.
Base the identification on tangible things in the application domain. Use a behavioral approach and identify objects based on what participates in what behavior. Use a scenario-based analysis. The objects, attributes and methods in each scenario are identified.
Okay. Okay, weather station description.
A weather station is a package of software-controlled instruments which collects data, performs some data processing and transmits this data for further processing. The instruments include air and ground thermometers, an anemometer, a wind vane, a barometer and a rain gauge. Data is collected periodically.
Okay.
When a command is issued to transmit the weather data, the weather station processes and summarizes the collected data. The summarized data is transmitted to the mapping computer when a request is received.
Okay, so let's see the weather station object classes.
Weather station object classes. Object class identification in the weather station system may be based on the tangible hardware and data in the system. Ground thermometer, anemometer, barometer. Application domain objects that are hardware objects related to the instruments in the system. Weather station. The basic interface of the weather station to its environment, it therefore reflects the interactions identified in the use case model. Weather data. Encapsulates the summarized data from the instruments.
Okay, so this is the image of
Weather
the,
station object classes.
this is how they are represented. So there is identifier in the weather station. You see the identifier is a property. It holds the ID of the weather station. For example, report weather is a method, report status is a method, and they are not taking any values as input. Power save is a method that takes the instruments probably as an array, and it starts power saving on all these instruments that has been sent as an input. Remote control is a method that takes commands to execute. Reconfigure is a method that takes commands. Restart is a method that takes instruments list to restart them. Shutdown is a command that takes instruments as a input. And on the weather data, there are properties such as air temperatures. This can be a list of double, for example. Ground temperatures, this can be a list of array of double. Wind speeds, wind directions. Wind speeds can be also an array of double, and wind directions can be enum or string. I don't know how, it depends on how they were defined. Pressures, rainfall, these are all properties, and these are the methods that weather data has: collect and summarize. And ground thermometer, it has two properties, the identifier and the temperature, and it has get and test data methods. Anemometer has three properties and it has two methods. Barometer has three properties and two methods. So this is the object classes. In your project, I want you to compose all of the object classes such as this one. Okay. It is also written in the project document. Let me show you. Let's open the project we have given you. Okay, find the project details here and let's download it. Okay, I think I have written this somewhere. Okay, it is written as chapter, but I have to fix them as lecture. I will do that. Okay, chapter 7, page 19, which is being here, as you can see. Let me fix it in a moment. So chapter will be replaced as lecture. Okay, and let's save as. Okay, it is getting uploaded. Let's continue. So the design models.
Design models show the objects and object classes and relationships between these entities. Static models describe the static structure of the system in terms of object classes and relationships. Dynamic models describe the dynamic interactions between objects.
Okay, examples of design models. Let's see them.
Subsystem models that show logical groupings of objects into coherent subsystems. Sequence models that show the sequence of object interactions. State machine models that show how individual objects change their state in response to events. Other models include use case models, aggregation models, generalization models, etc.
So there are different models for almost everything. And let's see the subsystem models.
Shows how the design is organized into logically related groups of objects. In the UML, these are shown using packages, an encapsulation construct. This is a logical model. The actual organization of objects in the system may be different. Sequence models. Sequence models show the sequence of object interactions that take place. Objects are arranged horizontally across the top. Time is represented vertically, so models are read top to bottom. Interactions are represented by labeled arrows. Different styles of arrow represent different types of interaction. A thin rectangle in an object lifeline represents the time when the object is the controlling object in the system.
Okay, so this is how the sequence model is drawn, and let's see it. So this is the sequence diagram describing data collection. So whether information system is an actor, therefore it is displayed like this, and the actor requests report from where satellite communications probably, and the satellite communication says that okay, acknowledge, I got your request. Then it requests report weather from weather station. Weather station acknowledges and says, okay, I'm preparing your report. And the weather station gets summary of the values that will be reported from communications link, and communication links generates summarization of weather data, and weather data returns the prepared data to the communications links. The communication links return prepared data to the weather station. Weather station sends back the report to satellite communications. Satellite communications acknowledges the weather station, so that weather station can end the execution of the command. Then satellite communications reply the report to the actor, the weather information system, and weather information system acknowledges that the report is received. This is the sequence diagram describing the data collection of the wilderness weather station.
State diagrams. State diagrams are used to show how objects respond to different service requests and the state transitions triggered by these requests. State diagrams are useful high-level models of a system or an object's runtime behavior. You don't usually need a state diagram for all of the objects in the system. Many of the objects in a system are relatively simple, and a state model adds unnecessary detail to the design.
Okay, so let's see this state diagram of the weather station.
Weather station state diagram.
Okay, so which states there can be in a weather station? It can be shut down, it can be configuring, it can be controlled, it can be running, it can be collecting, it can be testing, it can be transmitting, and it can be summarizing. Okay, so if the state is shut down, what commands you can use? We can use reconfigure command if the state is shut down. We can use power save command, and if after these commands are executed, for example, let's say the state is shut down and you have sent reconfigure command. In that case, the state goes into the configuring command. Okay. And when configuration is done here, it goes to the running state. And if, let's say, the system is shut down, then you can send restart command. And after restart command is sent, the state goes back into the running. And if the state is running, you can send shutdown command. And in that case, the state will go to the shutdown. So let me show you with some painting. Okay, so let's say our state is currently shut down. Okay, and okay, let's say our state is shut down. If our state is shut down, we can execute these commands, and these commands would bring our state into the configuring. Okay, like this. It goes to here. I mean, from this state, these commands can be executed, and after that, the state will become configuring. And once the configuration is done, it will go into the running state like this. Okay. And once the state is running, there are how many commands we can execute? Let's count them. 1, 2, 3, 4, and 5. There are 5 commands that we can execute when the state is running. First command is shutdown, which goes into the shutdown state. Second one is collecting, I mean the clock. So if you send clock command, it will go into the collecting state, and you can send remote control command. It will go to the controller state, and you can send report status command. And if you execute report status, it will go into the testing state. And if you execute the report weather command here, it will go into the summarizing state. So in the collecting state, you can execute only one command, which is collection done command. And in the control state, there is no command else in this diagram. And on the testing state, you have test complete. By the way, some of these are not commands, but rather, let's say, feedbacks. I just noticed that. So for example, the configuration done is not a command. It is a status. It is, let's say, automatically executed. Once the configuration is done, it automatically goes back into the running state. The commands are displayed like this. You see, this is a opening and closing brackets of methods that we do in programming. So these are commands that can be executed, and these are more like the events that happens after a certain time or process. So these are, let's draw them differently. Okay, these are commands that can be executed from the related states. And let's do the triggering events, for example. So this is an event. Oh, okay, let's make it. And this is an event. By the way, from running to collecting, you see there is no command. It is interval based. That is why clock. Interval based. Okay. So I think you are now understanding the difference. This is, for example, an event. When the weather summary is complete, it goes into the transmitting state. When the test is completed, it goes into the transmitting state and such. This is a pretty definitive description of the weather station state diagram. It is well designed, well prepared. Okay, let's continue.
Interface specification. Object interfaces have to be specified so that the objects and other components can be designed in parallel. Designers should avoid designing the interface representation but should hide this in the object itself. Objects may have several interfaces which are viewpoints on the methods provided. The UML uses class diagrams for interface specification, but Java may also be used.
Okay, so let's see the weather station interfaces. So interface reporting. Weather report, which takes WS identifier, which means weather station identifier. You provide weather station ID to the weather report method, and weather report method provides you back weather report. And same for status report, it takes the weather station identity ID and based and it goes to that station and gets the status report. And interface remote control, so the remote control is same. You can execute the start instrument command method, and it takes the instruments list or ID, and it returns back you the status of the instrument. If you have sent start command, it is expected to get back running status, and if you send stop command, it is expected to get back stopped status. Collect data is same and provide data is same. Okay, so what are the key points of the chapter 1?
Software design and implementation are interleaved activities. The level of detail in the design depends on the type of system and whether you are using a plan-driven or agile approach. The process of object-oriented design includes activities to design the system architecture, identify objects in the system, describe the design using different object models, and document the component interfaces. A range of different models may be produced during an object-oriented design process. These include static models, class models, generalization models, association models, and dynamic models, sequence models, state machine models. Component interfaces must be defined precisely so that other objects can use them. A UML interface stereotype may be used to define interfaces.
Okay, so we will start part 2. I'm going to take a break. Okay, so we are continuing. Design patterns.
Design patterns. A design pattern is a way of reusing abstract knowledge about a problem and its solution. A pattern is a description of the problem and the essence of its solution. It should be sufficiently abstract to be reused in different settings. Pattern descriptions usually make use of object-oriented characteristics such as inheritance and polymorphism. Pattern elements.
Name. A meaningful pattern identifier. Problem description, solution description.
Not a concrete design but a template for a design solution that can be instantiated in different ways.
Consequences and
the results and trade-offs of applying the pattern.
Okay.
The observer pattern.
These were the pattern elements, and now we are going to see that the observer pattern. Name, observer, description, separates the display of object state from the object itself. Problem description, use it when multiple displays of state are needed. Solution description, see slide with UML description. Consequences, optimizations to enhance display performance are impractical. So this was the observer pattern, and let's see the tabular view of the observer pattern.
The observer pattern 1.
Okay, pattern name and observer description.
Separates the display of the state of an object from the object itself and allows alternative displays to be provided. When the object state changes, all displays are automatically notified and updated to reflect the change.
Okay, problem description.
In many situations, you have to provide multiple displays of state information, such as a graphical display and a tabular display. Not all of these may be known when the information is specified. All alternative presentations should support interaction, and, when the state is changed, all displays must be updated. This pattern may be used in all situations where more than one display format for state information is required and where it is not necessary for the object that maintains the state information to know about the specific display formats used.
Okay, so solution description.
This involves two abstract objects, subject and observer, and two concrete objects, concrete subject and concrete object, which inherit the attributes of the related abstract objects. The abstract objects include general operations that are applicable in all situations. The state to be displayed is maintained in concrete subject, which inherits operations from subject, allowing it to add and remove observers. Each observer corresponds to a display, and to issue a notification when the state has changed. The concrete observer maintains a copy of the state of concrete subject and implements the update interface of observer that allows these copies to be kept in step. The concrete observer automatically displays the state and reflects changes whenever the state is updated.
Okay, what are the consequences?
The subject only knows the abstract observer and does not know details of the concrete class. Therefore, there is minimal coupling between these objects. Because of this lack of knowledge, optimizations that enhance display performance are impractical. Changes to the subject may cause a set of linked updates to observers to be generated, some of which may not be necessary. Multiple displays using the observer pattern.
Okay, so there are two different displays for the same subject here, which is a pie chart and column chart here. So observer 1 sees the subject as pie chart, and observer 2 sees the subject as a column chart. And you see how they are differently displayed. However, it is the same data. Okay, like this. And now we will see the UML model of the observer pattern. This is the multiple displays. This is how it will be displayed. Okay, there is concrete subject which has get state method and subject state as property. There is subject attach method which takes observer, detach method which takes observer, and notify which takes no parameters. And when you execute the notify method, for all or in observers or update. So all observers are notified. And there is observer, as you can see, which has update method. And there is concrete observer, which has update method and observer state. Okay, this is how it is shown in the UML. Concrete observer and concrete subject are the instance of classes, and these are more likely the classes. Okay, subject and observer are the class, and concrete observer and concrete subject are the instance of classes. I don't know if the arrows are the meaning of arrows are displayed anywhere. Let's check it out. Okay, inheritance, yes. This arrow means inheritance. So these are probably subclasses of the abstract parent classes. So these are inherited. Concrete subject is inherited from subject, and concrete observer is inherited from observer. So these are more generalized parent classes, and these are the inherited child classes, subclasses. Okay. You can also see the meaning of arrows somewhere here. I think it is displayed here. Okay, UML relations notation. Composition, aggregation, dependency, realization, implementation, inheritance, association. Okay, design problems.
To use patterns in your design, you need to recognize that any design problem you are facing may have an associated pattern that can be applied. Tell several objects that the state of some other object has changed. Observer pattern. Tidy up the interfaces to a number of related objects that have often been developed incrementally. Facade pattern. Provide a standard way of accessing the elements in a collection, irrespective of how that collection is implemented. Iterator pattern. Allow for the possibility of extending the functionality of an existing class at runtime. Decorator pattern.
Okay, let's see if 1 moment. Okay.
The observer pattern is a software design pattern in which an object, named the subject, maintains a list of its dependents, called observers, and notifies them automatically of any state changes, usually by calling one of their methods. It is mainly used for implementing distributed event handling systems in event-driven software. In those systems, the subject is usually named stream of events or stream source of events, while the observers are called sinks of events. The stream nomenclature alludes to a physical setup where the observers are physically separated and have no control over the emitted events from the subject stream source. This pattern then perfectly suits any process where data arrives from some input, rather ISN_T available to the CPU at startup, yet can arrive at random. HTTP requests, GPIO data, user input from keyboard, mouse, distributed databases and blockchains. Most modern programming languages comprise built-in event constructs implementing the observer pattern components. While not mandatory, most observers implementations would use background threads listening for subject events and other support mechanisms provided by the kernel. Linux EPOL.
Okay, there is Java, Kotlin. Let's check the C# one. So these are the example. Let's Okay, there is payload class which has a public property as message. There is a subject which inherits from iObserver payload. So iObserver is let's see the original of the article. Defines a provider for push-based notification.
The object that provides notification information, this type parameter is covariant. That is, you can use either the type you specified or any type that is more derived. For more information about covariance and contravariance, see covariance and contravariance in generics.
Okay, so the type is also defined here. And there is list of observers, there is subject, there is subscribe and subscribed. It's related to the observer list, which was an iObserver payload list. And when you send a message, you see it defines a new payload here, a message, and they are sent to the observer with on next. And there is unsubscribe, there is observer class, and you see it has public methods such as on completed, on error, on next. You see it sends message with on next like this, and it updates the message from here. This is being done automatically, and okay, a bigger software is needed to understand better, probably. Okay, you see on JavaScript it is easier to understand. We grab the button reference like this, then we create an observable of button click like this from event button click, and now we can subscribe an event to the click event like this. When a click happens, now we will get subscription constant. Okay, now we will get console log event. Okay, whenever a click event happens, it will automatically log the event. Okay, so there is Facade Pattern, which is, let's look for it on the Wikipedia.
The facade pattern, also spelled facade, is a software design pattern commonly used in object-oriented programming. Analogous to a facade in architecture, a facade is an object that serves as a front-facing interface masking more complex underlying or structural code. A facade can improve the readability and usability of a software library by masking interaction with more complex components behind a single and often simplified API. Provide a context-specific interface to more generic functionality, complete with context-specific input validation. Serve as a launching point for a broader refactor of monolithic or tightly coupled systems in favor of more loosely coupled code. Developers often use the facade design pattern when a system is very complex or difficult to understand because the system has many interdependent classes or because its source code is unavailable. This pattern hides the complexities of the larger system and provides a simpler interface to the client. It typically involves a single wrapper class that contains a set of members required by the client. These members access the system on behalf of the facade client and hide the implementation details.
Okay. Okay, there is facade, client, class. Client 1, client 2, facade, do something. There is a C++ example. There is struct, stock memory. Okay, basically facade design is what we normally use. We don't show everything to the client. We just provide the only necessary data, and the complexier things are kept in background, in private. Okay, there is Iterator pattern. Let's check it out too.
In object-oriented programming, the iterator pattern is a design pattern in which an iterator is used to traverse a container and access the container's elements. The iterator pattern decouples algorithms from containers. In some cases, algorithms are necessarily container-specific and thus cannot be decoupled. For example, the hypothetical algorithm search for element can be implemented generally using a specified type of iterator rather than implementing it as a container-specific algorithm. This allows search for element to be used on any container that supports the required type of iterator.
Okay, there are more information related to iterator pattern. Okay. For example, for each usage is being iterator pattern, I think, yes. And decorator pattern.
In object-oriented programming, the decorator pattern is a design pattern that allows behavior to be added to an individual object, dynamically, without affecting the behavior of other objects from the same class. 1. The decorator pattern is often useful for adhering to the single responsibility principle, as it allows functionality to be divided between classes with unique areas of concern. 2. The decorator pattern is structurally nearly identical to the chain of responsibility pattern, the difference being that in a chain of responsibility, exactly one of the classes handles the request, while for the decorator, all classes handle the request.
Okay. Interesting. So this is being decorated pattern.
The decorator pattern is a pattern described in the design patterns book. It is a way of apparently modifying an object's behavior by enclosing it inside a decorating object with a similar interface. This is not to be confused with Python decorators, which is a language feature for dynamically modifying a function or class. 7.
Okay, apparently, you see there is iBike interface, and aluminum bike is let's say inheriting iBike interface, and there is carbon bike which also inherits iBike interface, and there is abstract class bike accessories which also inherits iBike, and you see it has these, and there is security package which inherits bike accessories, and there is support package which inherits bike accessories, and from here it gets aluminum bike, then upgrades it with support package. From aluminum bike to support package, here they both inherit the iBike. Here, as you can see, it has a method over constructor from iBike. Therefore, you can define it like this, and you can upgrade it with new security package here, which also takes iBike. Okay, I am explaining these inheritance and polymorphism in the object-oriented programming. These are separate courses. Problems. Okay.
Implementation issues. Focus here is not on programming, although this is obviously important, but on other implementation issues that are often not covered in programming texts. Reuse. Most modern software is constructed by reusing existing components or systems. When you are developing software, you should make as much use as possible of existing code. Configuration management. During the development process, you have to keep track of the many different versions of each software component in a configuration management system. Post-target development. Production software does not usually execute on the same computer as the software development environment. Rather, you develop it on one computer, the host system, and execute it on a separate computer, the target system.
Okay, so reuse is really important. You should also follow this approach. And configuration management. This can be done with a code management system such as using GitHub and Git Bash, like this, committing each version and such. Host target development. This is also important, especially in mobile programming, because every mobile device may act differently, since almost every brand make customizations to their Android version, or there may be differences between different iOS versions and such. These are all important implementation issues. So let's start with reuse, which is very important.
From the 1960s to the 1990s, most new software was developed from scratch, by writing all code in a high-level programming language. The only significant reuse or software was the reuse of functions and objects in programming language libraries.
And because of this, people were able to by alone develop a operating system. I believe the first 1 minute. Okay, and okay, let's continue.
From the 1960s to the 1990s, most new software was developed from scratch, by writing all code in a high-level programming language.
Okay, so in the past, the demand of the users were much lower than today, because you had to develop your software from scratch, and which was preventing very highly developed and complex software to be programmed. For example, I believe there are even operation systems that are coded by a single person. And let's try to find. Okay, there's a question on Quora. Okay. Okay. Okay, there are even games developed by a single person. However, most of them would be primal at the moment, but okay, there's Undertale. You see, okay. a game like this. But I believe the older software were not developed by a lot of developers. For example, let's check the first team of DOS. Okay, so let's read the history of DOS. You see, even the name was like this.
Quick and dirty operating system.
I think, and okay, anyway, I couldn't find it at the moment, but in the past it was much easy to develop simple software and sell it because the expectation of the customers were lower. However, in today, for example, from games, PC games, very high quality of graphics are expected, and from any software, high performance and a lot of features are expected. So in today's software engineering, you have to use ready code and ready libraries to raise the expectation. Okay, to provide quality software for the demand. Okay.
Costs and schedule pressure mean that this approach became increasingly unviable, especially for commercial and internet-based systems. An approach to development based around the reuse of existing software emerged and is now generally used for business and scientific software.
Okay, there are reuse levels, the abstraction level.
At this level, you don't reuse software directly but use knowledge of successful abstractions in the design of your software.
The object level.
At this level, you directly reuse objects from a library rather than writing the code yourself.
At the component level.
Components are collections of objects and object classes that you reuse in application systems.
And there is system level.
At this level, you reuse entire application systems.
Okay, one moment. Okay, so reuse costs.
Reuse costs. The costs of the time spent in looking for software to reuse and assessing whether or not it meets your needs, where applicable, the costs of buying the reusable software. For large off-the-shelf systems, these costs can be very high. The costs of adapting and configuring the reusable software components or systems to reflect the requirements of the system that you are developing. The costs of integrating reusable software elements with each other, if you are using software from different sources, and with the new code that you have developed.
Okay, so these were related to reuse. Now the configuration management.
Configuration management is the name given to the general process of managing a changing software system. The aim of configuration management is to support the system integration process so that all developers can access the project code and documents in a controlled way, find out what changes have been made, and compile and link components to create a system. Configuration management activities. Version management, where support is provided to keep track of the different versions of software components. Version management systems include facilities to coordinate development by several programmers.
This is really important, and to be able to achieve this, it is best to use code management systems such as using GitHub and Git Bash. That is why it is important for you to use GitHub or Bitbucket and Git Bash or similar program to do a version having software development in the project that I have gave you as a semester project for this course. Okay, so let's open our GitHub. I think I have written it there as well, but I will just be sure. Yes, the project has to be developed by using GitHub or Bitbucket code management system, or similar ones are also accepted as long as they are you are using a code management and having a versioning. Okay, I will just also add it. Okay. Let's push these as well to our GitHub repository. So this is actually versioning, as you can see here. Commit details. I could have give abstract numbers as well, but I didn't do it.
Problem tracking, where support is provided to allow users to report bugs and other problems, and to allow all developers to see who is working on these problems and when they are fixed.
Okay, this is also important for on GitHub, for example, there are issues, and you can post issue or anyone can post issues as well. This is a good way of handling issues and problems. And the other one, host target development.
Host target development. Most software is developed on one computer, the host, but runs on a separate machine, the target. More generally, we can talk about a development platform and an execution platform. A platform is more than just hardware. It includes the installed operating system plus other supporting software such as a database management system or, for development platforms, an interactive development environment. Development platform usually has different installed software than execution platform. These platforms may have different architectures. Development platform tools. An integrated compiler and syntax-directed editing system that allows you to create, edit and compile code, a language debugging system, graphical editing tools, such as tools to edit UML models, testing tools, such as Junit that can automatically run a set of tests on a new version of a program, project support tools that help you organize the code for different development projects.
Okay, for example, for this we can give example of Visual Studio. For this, we can also give example of Visual Studio and such. Okay, it is also coming here.
Integrated Development Environments, IDEs. Software development tools are often grouped to create an integrated development environment (IDE), and IDE is a set of software tools that supports different aspects of software development within some common framework and user interface.
For example, Microsoft Visual Studio.
IDEs are created to support development in a specific programming language such as Java. The language IDE may be developed specially, or may be an instantiation of a general-purpose IDE, with specific language support tools. Component system deployment factors. If a component is designed for a specific hardware architecture, or relies on some other software system, it must obviously be deployed on a platform that provides the required hardware and software support.
Because of this, usually big software systems are sold with their hardware and operating system as well. For example, let's say you are purchasing a hospital management system, and usually in those cases the seller of the software also sells you the server as well. Okay, and that ensures compatibility and errorness. However, it also increases your costs.
High availability systems may require components to be deployed on more than one platform. This means that, in the event of platform failure, an alternative implementation of the component is available. If there is a high level of communications traffic between components, it usually makes sense to deploy them on the same platform or on platforms that are physically close to one another. This reduces the delay between the time a message is sent by one component and received by another.
For example, let's say you have multiple databases to communicate, and in that case, being in the same physical place would reduce your network communications delay.
Open source development. Open source development is an approach to software development in which the source code of a software system is published and volunteers are invited to participate in the development process. Its roots are in the Free Software Foundation, www.fsf.org, which advocates that source code should not be proprietary but rather should always be available for users to examine and modify as they wish. Open source software extended this idea by using the internet to recruit a much larger population of volunteer developers. Many of them are also users of the code.
For example, let's open the main page of GitHub, which is very widely used for open source development. Let's see, there are trending. Okay, for example, all of these are open source software systems that are being developed by multiple developers. For example, let's find a good one. Okay, native script, and let's see how many contributors. It is used by over 2,000 people, and around 200 people developer is contributing to this open source. Reading open source software will also improve your developing skills a lot, because people here are usually follows the best software development approaches. Let's look for some C# project. Okay, and from here can we sort them? Okay, let's by most stars. Okay, Rosalyn, it is a compiler, and how many developers? You see over 400 contributors, and Stream Farm. Okay, there's faster. What is this? Let's find a crawler, which I use a lot. Okay, and let's sort by most starts. Okay, there is open source. This is written in, by the way, C++. Okay, there is infinity crawler. Let's look for it. And let's check the sources by src. Okay, for example, crawling class. Okay, let's check it out. It has only one class definition and crawled result, for example, here, and crawl settings. You see here a class, and there is crawler CS. Okay, you see this is the crawler CS. It has commands, and you can learn a lot of programming practices from such good projects. I don't know how many person is contributing to this project. Usually you should look for high contributor count having projects to improve yourself. Okay, only 2 contributors. So this is rather a single person project. Okay, and anyway, you get the idea. I don't know if we can sort by number of contributors. Try to find, and perhaps the most forks. Okay, Scrappy. Oh, I will check for C# by the way. In the open source development, I think Python is the number 1 currently. You see the number of Python repositories. Okay, there is .NET Spider, which has 20 contributors, and from here, okay, there is agent, program CS. Okay, you see it uses task factories, start new, it is asynchronous. Anyway, you get the idea of open source development. Participating in open source development is extremely useful. It improves your skills, it improves your group working abilities. It can help you tremendously in your professional life. You can also show it in your CV. It can benefit you from that point as well.
Open source systems. The best known open source product is, of course, the Linux operating system, which is widely used as a server system and, increasingly, as a desktop environment. Other important open source products are Java, the Apache web server, and the Mysql database management system.
For example, let's check the Linux on GitHub. I don't know if it is there. And you see 5,000 plus. Okay, there are, I think, 16,000 contributors for Linux, and you see it has about 1 million comments, 1 million versioning. You can also think it as that. It is frequently getting updated. Okay, this is a huge project. Let's see if we can find MySQL. Yes, MySQL is there. MySQL server. Let's check it out. Okay, so, this is not real MySQL. Or maybe it is, I don't know. I think they allow only official staff to contribute to this, probably, because it has very lesser number of contributors. So you see the used languages in this project, mostly C++. Anyway, let's continue.
Open source issues. Should the product that is being developed make use of open source components? Should an open source approach be used for the software's development?
I usually do use open source libraries and frameworks.
Open source business. More and more product companies are using an open source approach to development. Their business model is not reliant on selling a software product but on selling support for that product. They believe that involving the open source community will allow software to be developed more cheaply, more quickly, and will create a community of users for the software.
So this is really important. Okay.
Their business model is not reliant on selling a software product but on selling support for that product.
For example, MySQL is still free. However, the support is not. This is a good example of that. Okay, you see when we click the how to buy, I think it is more about the support of MySQL. You see it says services. You see MySQL subscription licenses, support and training. And okay, let's click the services. So you see MySQL training, MySQL certification, MySQL consulting, and MySQL support. All of these are services, not the product itself. Okay, this is a very good example of this approach.
Open source licensing. A fundamental principle of open source development is that source code should be freely available. This does not mean that anyone can do as they wish with that code.
Okay.
Legally, the developer of the code, either a company or an individual, still owns the code. They can place restrictions on how it is used by including legally binding conditions in an open source software license. Some open source developers believe that if an open source component is used to develop a new system, then that system should also be open source. Others are willing to allow their code to be used without this restriction. The developed systems may be proprietary and sold as closed source systems.
Okay, license models. This is also important.
License models. The new General Public License (GPL). This is a so-called reciprocal license that means that if you use open source software that is licensed under the GPL license, then you must make that software open source. The new Lesser General Public License (LGPL) is a variant of the GPL license where you can write components that link to open source code without having to publish the source of these components. The Berkeley Standard Distribution (BSD) license. This is a non-reciprocal license, which means you are not obliged to republish any changes or modifications made to open source code. You can include the code in proprietary systems that are sold. License management. Establish a system for maintaining information about open source components that are downloaded and used. Be aware of the different types of licenses and understand how a component is licensed before it is used. Be aware of evolution pathways for components. Educate people about open source. Have auditing systems in place. Participate in the open source community.
Okay, so the key points of the chapter 2.
When developing software, you should always consider the possibility of reusing existing software, either as components, services, or complete systems. Configuration management is the process of managing changes to an evolving software system. It is essential when a team of people are cooperating to develop software. Most software development is host-target development. You use an IDE on a host machine to develop the software, which is transferred to a target machine for execution.
Yes, an IDE example example is Visual Studio, for example.
Open source development involves making the source code of a system publicly available. This means that many people can propose changes and improvements to the software.
Okay, you see this is an ID, and an integrated software development environment of Microsoft, and currently Microsoft is releasing Community Edition, which is for free to use. You can use the Community Edition of Microsoft Visual Studio for free. This is the best IDE available for software development, as my belief, so I prefer that. Okay, so end of the lecture. Hopefully see you next week. Please try to avoid coronavirus because it is getting more wider and wider. I mean, it is infecting more people and more people, so we should try to avoid it as much as possible. If it is not absolutely necessary, we should not go out. Okay, you know the issue. Hopefully see you next week. End of lecture.